Today we're going to talk about domain and range, and specifically what we're going to do is we're going to look at the domain and range with respect to a graph. But we need to review just a real quick couple of concepts. When we're dealing with domain and range, we're still dealing with inputs, and the set of inputs that result in an output is called the domain of the function. When we get our outputs, what we're working with are the range. And if I want to get a little bit more specific here, the inputs, the domain, are the x values, and the outputs, the range, are the y values of the function. A couple other things here. We yesterday talked specifically about interval notation, and I also want to introduce you to set builder notation. We're going to use it a little bit, but mostly when we're working with graphs, we use interval notation. But interval notation looks something like negative infinity to 4, or 4 to infinity. It could also be two numbers. It could be something like 2 to 10. Those are just some of the examples. Remember, infinity always has a parentheses, and the number might have a square bracket. And a square bracket means that it is included in the answer, and a parentheses means that it is not included in the answer. But the other type of notation is set builder notation, and the first thing that we do is we make a squiggly parentheses. So it's a bracket, and then we say something, we say x bar, and what that means is that for all values of x such that, in this case we could say x is less than or equal to 4. That's a set builder notation. Most of the time when we're dealing with set builder notation, however, we do squiggly bracket, and we still do the x bar, but then we have a bunch of points or values like 1, 2, 5, 9, something like that. More often we use the second way here with that set builder notation as opposed to the first, because when we use that first method up here in set builder notation, we're better off using the interval. But we'll deal more with set builder later. But again, what we're looking at today is we're specifically looking at a graph and identifying what's the domain and the range of the graph. The nice part on this one is that we have a definite starting point over here to the left, and we have a definite ending point over here to the right, where there's endpoints. There's physical points right there on the ends of the graph. We're given this function g of x, and we want to, for part A, determine the minimum and the maximum x values represented on the graph. Minimum means the least value. Maximum means the most value, and it's specific here. We're looking at the smallest x value and the biggest x value. So what's the smallest x value on this graph? Well, we look farthest to the left and we see that the smallest x value is -3. But we also have to find the maximum value, so we're going to look towards the right, and in fact we're going to go farthest to the right. And as we count over, 1, 2, 3, 4, 5, 6 is going to be our maximum, biggest x value on the graph. And then we can state the domain using our interval notation. Well, -3 is part of a point on the graph, and +6 is part of a point on the graph. So our interval notation It's going to look like an ordered pair, except that we're going to have square brackets. And once again, in the italics there, this illustrates that the domain goes from the smallest x value on the graph to the largest x value on the graph. We can do the same thing for the range, for the y values on the graph. We want to find the smallest, the minimum, and the maximum y values represented on the graph. In other words, what's the lowest y value on this graph? So we go to the lowest point here and we count down 1, 2, 3, 4, -5 is our minimum. And then what's our highest y value? What's our biggest y value on this graph? It's actually 1, 2, 3, 4. And then we can write that in interval notation. Once again, those are values that are on the graph, so it's going to look like an ordered pair, except that we're going to have square brackets on this. One other quick technique that I want to show you that we can use on this one, because we happen to have a definite starting point and a definite ending point on here, is you could draw a rectangle around this graph. And when you do, farthest to the left and farthest to the right, that gets us our domain. Lowest to highest gets our range. And we can do that again because we have a starting point and we have an ending point on this graph. That's not always the case, as we look at the next example. The graph above, and most of our graphs, is continuous. CONTINUOUS, meaning that we could put our pencil on one end of the graph and we can draw the entire graph without lifting our pencil up. The following graph that we're going to deal with here is not going to be continuous, and when we don't have a continuous function, then we need to use set builder for our domain and range. But as we look at this next one here, this is one type of graph where it's easier to use set builder notation rather than interval notation to write the domain and the range. And what it is, it's a graph, as we can see, that's got 1, 2, 3, 4 points on it. So the first thing that we can do on this graph is we can list the ordered pairs from the graph. They don't have to be in the same order as me, but we want to make sure that we list them all if you're working ahead. But I went farthest to the left, so -5, -3. And then another point, -3, +3. Another point, -2, +5. And 1, 3. Again, you don't have to have them in the same order. You just want to make sure to have all 4 of those points. I'm sorry? And thank you. -1. Once we get the ordered pairs listed correctly, is this graph a function? Notice, -5, -3, -2, -1. No x repeats, so yes, it is a function. Is it 1-to-1? No, because we've got a 3 for a y value in our second point, and we have 3 for a y value in our fourth point. The y values repeat, so no. It fails the horizontal line test is another part of this. But now that we've got that, we want to write our domain, and again, we're going to use our set builder notation, so we're going to use our squiggly parentheses there, and we're going to list the x values. But remember, it's x bar for all values of x such that x equals -5, -3, -2, and -1. That's all our x values listed from our ordered pairs there. Well, the range, we're going to do the same thing, except that we're dealing with the y values, and hopefully you can fit your spacing in a little bit better than me. Squiggly parentheses. But remember, range is represented by the letter y, so we're going to have y bar, and then it's going to be y equals -3, +3, and 5, squiggly parentheses. We don't need to write the 3 again. It's a repeated value. So there's our domain and range of this function, but not one-to-one. When we've got ordered pairs, that's when we use that set builder notation. Some functions, defined with graphs or equations, have domains and ranges that stretch out to infinity, like the parabola here in our next example. So here's a parabola represented by that function, x squared minus 2x minus 3. We want to come up with the domain and the range, written in interval notation. Well, for problems with domain and range, looking down here at the star part here for a moment, for problems like this, that have arrows on the graph, our domain and range could stretch to infinity. So we're going to keep going on and on and on in direction to indicate the infinity here. So if we look at this problem here, or look at our possible answers to help us, looking at our domain, it says from -2 to 4. But does our graph stop there? No, we have arrows on the end. It's going to keep going. So we know that it's not 1, and we know that it's not 2. Now on part 3 here, it says that we're going to go from -infinity to +infinity. As I draw on this graph, the thing to notice is that when we continue, because we have arrows, so we just have a piece of the graph drawn, our graph continues to go outward. And because it continues to go outward, that means that our domain is going from -infinity to +infinity. It's not just stopping with what we have in the picture. It's going to keep going. I'm pointing towards the left and I'm pointing towards the right. It's going to keep going out as it keeps going up. So this is our answer here. But what I find easier to see with respect to this graph is the range. And oftentimes the way I look at the range is, do we have a high point or do we have a low point in this graph? If we look over here at the graph, we have a low point. Our low point is at -4. And the graph is going to continue to go upward, and we've got arrows pointing upward. It's not going to stop, so it's going to continue to go to infinity. The -4 is on the graph, so we have to have the square bracket, and then infinity always has parentheses, which again will indicate that 3 is our correct answer on this particular problem. And our goal today is to be able to identify the domain and the range from a graph. So as we look at our last examples down here in section number 4, for the graphs below, we're going to state the domain and the range using interval notation. Remember, we only use set builder notation when we have a bunch of ordered pairs, a bunch of points. And as we look at this first example here, let's do the easy part first, which is the function. Is this graph a function? No. Is it one-to-one? Not one-to-one. Fails the vertical line test for the function, fails the horizontal line test for the one-to-one part. Our domain. when we're finding this, we're going to write it in interval notation. We look for the point farthest to the left. So if we look at our circle and we go farthest to the left, our circle is over here at -1. That's farthest to the left. We can go farthest to the right. 1, 2, 3, 4, 5. And those are both coming from points that are on the graph. So we're going to have square bracket. We do the same thing for the range. We're going to go to the lowest point on the graph, which is 1, 2, -3. And then to the highest point on the graph, which is 1, 2, 3. And again, those are both coming from points on the graph. So our range goes from there to there. If you like that rectangle version that I put on our first example, draw a rectangle. It'll be more square. But draw a rectangle around the circle. Go from left to right to figure out your domain. Go from bottom to top to figure out your range. Letter B. One thing that I might add in here that might help a little bit is putting a couple of points there on the end, because it is a continuous function, but it does have a starting point and an ending point. Is this graph a function? Yes. Is it 1-to-1? No. When we draw our horizontal line, we are going to cross more than once. Our domain. Look farthest to the left. We don't have any arrows on here, so we're not going to have infinity, negative infinity to infinity. Look farthest to the left. Our x value farthest to the left is 1. Our y value farthest to the right is 5. And again, those are both on the graph. Our lowest value for the range happens to be 0. Remember, the ordered pair of this point at 1 is we went right 1 space, but we went up nothing. That's a 1, 0. So our range is going to be 0. Our highest point on the graph is way up there at 6. And those are both coming from points on the graph. So we're going to have square brackets. Domain and range. Domain are the x values. Range are the y values. Domains are the inputs. Ranges are the outputs. As we look at letter C, is this a function? No. And based on the way that I taught you, if it's not a function, then I've said that it's not 1-to-1. If you were just looking at from a 1-to-1 perspective, this graph would pass the horizontal line test. But the way I said it is, if it's not a function, then it's not 1-to-1. So I'm going to stick with the way I taught you. But some other teachers taught it differently, so some other teachers might be saying yes. But when we look at our domain, the difference on this particular problem compared to the previous ones is, one thing, we've got arrows on it. So at some point in time, we're probably going to have an answer that's negative infinity to infinity, which means that it represents all of the numbers on the number line. Well, is our domain going to be negative infinity to infinity? And it isn't. Farthest to the left is this point here, which is 0. Now we are going to continue in the rightward direction forever and ever. It's pointing towards the right. So we are going to go to infinity. Remember, infinity always has parentheses. The 0 is a point on the graph. It's going to have a square bracket. Now, though, will it make sense that our range is negative infinity to infinity? And hopefully the answer is yes. We're going to continue going up with our graph. We're going to continue going down with our graph. We don't have a high point. We don't have a low point on the graph for our range. Another letter C. Is this a function? It is. Is it one-to-one? No. We've got arrows on this graph, so once again, something probably is going to have that notation in it. Is it going to be the domain? And it is. Once again, as I jumble up this picture, don't jumble up yours, because I can erase mostly, is that our graph, I didn't do very well. As we keep going downward, what happens is the graph keeps going outward. So it's going to encompass all of these values on the x-axis. So our domain is negative infinity to infinity. Our range is not. Once again, think of the range as, do we have a high point or do we have a low point on the graph? And what we have is we have a high point on this graph. And our high point, even though I missed it a little bit on here, is 4. And it's going to go from negative infinity to 4. Something to remind you of is when we're writing interval notation, we need to go from the smallest value to the largest value. So negative infinity, you can see my picture, I've drawn it, and it still has arrows on it. It's still going in the downward direction. It's going to continue to go downward. So we have negative infinity is going to be our lowest value, and then we're going to work our way up to our highest value, which is going to be the 4, and it's not going to go past that. 4 is a value on the graph, so it's going to have that square bracket. Letter D. Is it a function? Yep. Is it one-to-one? Yep. Both of those. But for unknown reasons to me, this is the hard one here. And once again, what we see on the end is we see arrows. So something, at least, is going to have negative infinity to infinity. What's the domain of any line with a slant? Well, the domain of any line with a slant is negative infinity to infinity. And what's the range with any line and a slant? It also is negative infinity to infinity. We actually wrote that down in our notes probably a week and a half ago or so. Because again, it should be one of those problems that you should know, but that's not necessarily true. And I recognize that. But any line with the slant has the domain and range of negative infinity to infinity. When we finish here on letter E, notice that letter E is a collection of points. So we need to use set builder notation on this one instead of the interval. But is this a function? I think so. Is it a one-to-one function? I still think so. And the worst comes to worst if we write down these ordered pairs, and I know that takes a little bit of time, but we have 1, 3. We have 2, 1. We have 3, negative 1. We have 4, 2. We have 5, 0. And we have 6, 6. So there's a list of ordered pairs. And once we have that, we're going to write down the domain, which is the inputs, which are the x's. And that's squiggly bracket x bar And x equals these values. 1, 2, 3, 4, 5, 6. Running out of space here. Squiggly bracket. The range are the set of y values. Again, squiggly bracket, y bar. For all values of y such that y equals, and then it's 3, 1, negative 1, 2, 0, 6. I am not picky about that order. If you happen to take math in college, your college professor probably will be. And maybe it's you as well. You want to say, well, negative 1, 0, 1, 2, 3, 6, if you want that in numerical order. But it's still representing the y values, which are the range.